tragic collapse strikes a Florida landmark.
A mouth has just dropped open. 1,200 foot, the bridge is gone.
In Germany, a groundbreaking design crashes to Earth.
And all of a sudden, a big crash happened, and the roof collapsed towards the street.
A troubled bridge in the capital of Denmark.
The engineering of it simply didn't work.
And a California dam threatens an epic flood.
Water was shooting out in multiple directions, so the whole face of the dam just looked like white water.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Gravity is one of the biggest enemies for engineers. And the larger the project, the greater the threat. Like this deadly catastrophe in Florida that no one saw coming.
This disaster was a reminder that you have to prepare for any eventuality.
A fatal flaw with devastating consequences.
You see wreckage hanging. You can see cars on the bridge.
A tragedy that left an entire community in shock.
The outside world had finally reached Tampa Bay. This was a monumental catastrophe.
And forced a change in the rules.
Lessons were learned so that a tragedy like this should never happen again.
Florida's Sunshine Skyway Bridge has stood as a proud reminder of the state's engineering prowess for more than 30 years. The bridge is the third and most successful span over these waters and marks the entrance to a 1,000 square kilometer sea inlet, Tampa Bay.
Tampa Bay is a large natural harbor connecting the west coast of Florida to the Gulf of Mexico. It's one of the longest shipping channels in the world and one of the most treacherous.
Not only is the channel busy and narrow, but bad weather can appear out of nowhere.
Florida is known as the Sunshine State, but it also experiences some of the worst storms in the U.S. In fact, 40% of all hurricanes hit the Florida coastline.
Something locals like author and reporter Bill DeYoung are all too aware of.
Well, it's a beautiful day out here on Tampa Bay. It's like this, I would say, 360 days a year. And what happens on the other 4 or 5 days of the year that it's not like this is weather comes in off the Gulf of Mexico. These squalls build up on the Gulf of Mexico.
That dramatic weather is the exact reason this third bridge was built. Its predecessors had long hidden a fatal flaw. The first Skyway Bridge was built in the 1950s, with a twin structure joining it in 1970. Both had long causeways leading to dramatic spans over the bay.
The first Sunshine Skyway Bridge went up in 1954 to cross 15 miles of South Tampa Bay. The overwater part of the bridge, the really scary part, is just over 4 miles. It did feel like you were going up into the clouds. It was so high.
To allow huge ships to pass beneath, the ski ramp approaches raised traffic 45 meters above the water onto the central span. Like many bridges of their time, the span consisted of a tried-and-true design known as a cantilever truss. Structurally, Boston's Tobin Bridge works the same way as the original Skyway. Engineer David Beck explains.
Both of those bridges were cantilevered truss bridges to create one big wide span. You have 3 main components: the cantilever section to the right, to the left, and then you have the center span which is coming up and supported off the cantilever trusses.
The 4 legs on a cantilever bridge, known as piers, provide support to the two bridge arms and the road above as they extend across the span. These four piers each serve a crucial role in balancing out the massive forces at play within the structure.
If you take a look over here, you can see the pier, that's the main pier onto it. It's got two columns coming up and then a cross brace just to keep the pier, giving it lateral resistance onto it. But it's basically those columns that are taking the load of the bridge and transferring it down to the bridge pier foundation.
From 1971, the twin Skyway bridges of Tampa towered over the water, carrying thousands of cars a day across the busy shipping lane. Although no one realized it, the bridge had a fundamental weakness. On the morning of May the 9th, 1980, the MV Summit Venture, a 185-meter-long freighter, was heading from the Gulf of Mexico to port in Tampa Bay. Using a simulator, Captain Ted Morley is accurately replicating the treacherous conditions the pilot was facing.
So we're seeing almost exactly the view that the pilot would have seen as he approached Sunshine Skyway Bridge. Tampa Bay is notoriously difficult to navigate because it's shallow, a lot of shallow areas around it. The channel itself is a deep cut, but the bay itself is very shallow. So you get a lot of tidal effect, a lot of current effect, and you also have a lot of weather coming off with rain, sleet.
Like all ships heading into Tampa Bay, the Summit Venture needed to make a 13-degree turn to navigate safely between the Sunshine Skyway's central span. This might not sound like much, but this ship is the length of 2 football fields.
Even on a clear day, navigating the channel isn't straightforward. But as it approached the bridge, the ship encountered an intense and localized storm known as a microburst.
When Summit Venture was coming in on the 9th of May of 1980, this black cloud literally followed it in from the Gulf, just hung over its head. It's what they call a macroburst storm. It's a little intense storm inside a squall.
So right now, as the rain intensifies, we're actually seeing the echo of the rain on the radar. And right now, it's still light. The rain is not super intense yet, but you can see how the rain itself is creating these echoes and this noise and clutter on the radar. That will actually get worse and worse. And modern radars have a better way of handling that than the older ones do, but that can actually obscure the entire view of the radar, rendering it absolutely useless.
The storm reduced visibility to 0 and was strong enough to blow the 20,000-ton freighter off course.
This pilot was effectively steering blind, and he had no idea he was on a catastrophic collision course.
Remember, this is 1980. There was no GPS yet. You have shipboard radar in case your visibility goes out. Well, the radar stops working, too. He's 7/10 of a mile from this bridge. It takes a mile for these ships to stop.
As soon as he realized the danger, the pilot dropped anchor and put the ship's engines into full reverse. But it was already too late. The Summit Venture rammed the southernmost pier of the bridge.
Much like, say, the Kennedy assassination or 9/11, people remembered exactly where they were when they heard about it. This is Tampa Bay's version of those horrible, horrific events.
At the time of the accident, Michael Rosselet was a volunteer rescue diver when the call came in.
So I got the pager call at about 7:30 in the morning, and we were told that a boat had hit the Skyway Bridge. So we were expecting, I think, just your average boat, maybe trawl or fishing boat, had run up against the bridge. We made that turn down toward the Skyway, and it's just gone. I mean, it's 1,200 foot, 1,500 foot of bridge is gone. Our mouths just dropped open. We thought, wow, this is much more than we were expecting.
With this vital support gone, a 400-meter section of the deck twisted and fell 45 meters into the bay below.
Several drivers were able to stop their vehicles in time before dropping into the void. One skidded to a stop barely 14 inches, about 35 centimeters from the edge.
Others hadn't been so lucky. 6 cars, a pickup truck, and a Greyhound bus had already fallen into the water. Michael and the rescue team quickly realized that the odds of any survivors were slim.
We see wreckage hanging, we could see cars on the bridge. But at this point, we just realized we had to kind of go into action. Saw the bus in the water. At that point, it was pretty obvious that it wasn't rescue, it was recovery.
In all, 35 people died in the disaster, with only one very lucky survivor.
Incredibly, one man survived when his pickup bounced off the deck of the ship below, breaking his fall into the bay. Those tiny margins were the difference between life and death.
This thing was sort of like the outside world had finally reached Tampa Bay. This was a monumental catastrophe that nobody could believe had happened because everyone drove over that bridge all the time.
So, was this just a tragic accident, or could more have been done to avert one of the worst catastrophes in Tampa's history? The official report into the disaster concluded that a complex series of factors, from the severe weather to human error, caused the accident. But, crucially, it also highlighted a flaw in the bridge: the lack of protection on the supporting piers against ship impact. And it turns out the Summit Venture hit the worst possible pier. Engineer David Beck explains.
Hitting one pier resulted in the collapse of actually 3 spans of the bridge. The reason why you had 3 spans collapsing on the Sunshine Skyway bridge, the center piers were pretty hefty. The back pier, since it was never designed to take on a collision with a ship, it had smaller piers into it. And when that back pier went out, the whole cantilever section of the bridge fell into it. When you lost the cantilever section on the one side, then your center span totally collapsed.
With the potential for such catastrophic consequences, not protecting the bridge itself would seem short-sighted, especially given this was not the first collision here.
Turns out the old Skyway Bridge had been hit 13 times by vessels before the Summit Venture crash. So it seems incredible that at the time of the collision, there were no requirements or standards for protecting bridge piers against ship impacts.
The bridge had survived the previous incidents with relatively minor damage. But a ship this large, striking the end pier, delivered the fatal blow.
I think it was an accident waiting to happen. It never occurred to them to protect this bridge from ship traffic. We were taking our lives into our hands every day by crossing this thing. It was a miracle it didn't happen before.
With the risk of another collision looming, the decision was made to replace the old bridges with a safer, more modern design.
Historically, bridge engineers have focused on making big exposed bridges safe from the forces of nature: earthquakes, hurricanes, tornadoes. But ship collision is a much greater threat than any natural disaster. So for the new bridge, they brought in one of the world's leading experts on bridge protection.
With safety at the forefront, the new Sunshine Skyway replaced the cantilever with a more robust cable stay bridge. To reduce the risk of collision, the bridge was positioned away from the treacherous 13-degree bend in the shipping lane.
The new bridge has been moved to facilitate an easier approach for the ships, so the ships can line up better to the bridge and be square to it before they proceed through it, and it gives them a little more lead time.
But it's what's going on beneath the deck that's turned this bridge into one of the safest in the world. An impact protection system made up of concrete islands known as dolphins.
Dolphins are usually made from steel or reinforced concrete. You have a number of poles driven into the bedrock, rising above the surface of the water and filled or connected to create large concrete islands. In effect, they're like bumpers or fenders for bridges.
The new Sunshine Skyway has 4 large dolphins, 60 feet or 18 meters in diameter, to protect the 2 main piers, and 32 smaller dolphins protecting the smaller piers, stretching beyond the edges of the shipping lane.
Each set of dolphins combined can withstand the impact of an 87,000-ton ship, around 4 times the size of the Summit Venture. And crucially, they're designed to stop a ship, not sink it.
As you see now, we have all these large dolphins or circular concrete abutments to deflect any traffic that would hit any of the spans. And I can't imagine anything hitting the Skyway now and not being deflected first.
In hindsight, it seems like an incredibly simple solution. If you want to stop ships from hitting the bridge, put something in their way. And they didn't stop there. 2 small rock islands surround the 2 main piers, so if a ship somehow manages to get past the dolphins, it will be grounded before it can do any damage.
There's also a guidance system for ships passing under the bridge, an early warning system for motorists, and sensors to detect even minor collisions. And the central span is now 50% wider, with a clearance of over 55 meters.
When designing a new bridge, the investigation's findings were clearly taken on board, and now the new Sunshine Skyway is one of the most well-protected bridges in the world.
Rising out of Tampa Bay in 1987, this stunning new design was a perfect addition to the Sunshine State coastline. With groundbreaking architecture, designers aim to make an impression on the outside world. But they can't overlook what's on the inside. Like this Congress Hall in Germany that suffered an epic failure.
With this build, they pushed the boundaries way too far.
A world-famous building destroyed in seconds.
Half of the whole roof was completely collapsed.
In 1980, Berlin is a city divided by the Cold War. Capitalism rules the West, communism the East. And a powerful icon of democracy is about to fall. In 1957, the Eisenhower administration offered to build a new cultural center in West Berlin. It was to be called the Congress Hall. Ann Meyer has worked here for over a decade.
The Americans wanted it to be seen as a bastion of the free speech, and it was their education program to teach Germans after World War II again free speech.
Unsurprisingly, the location was to be a stone's throw from the Berlin Wall.
It was a strategic decision to have a building that is as high as the Reichstag, that could be seen by the people from the West as well as from the East.
The building itself was a cultural statement. Its shape was unique and much admired.
For those entering the building, it must have felt like walking into the future. Inside there was a concert hall, galleries, a cafe. Conversation, culture, and ideas just circulated within its walls.
Berliners adored the building from the beginning onwards, and Berliners have the tendency to make nicknames for buildings, and they called this building Schwangere Auster, translates the pregnant oyster.
The architect, wanting to ensure the Congress Hall's signature curved roof was visible across the city, used a cutting-edge technique known as pre-stressed concrete construction. Many structures use concrete poured over steel bars or rebar to give it strength.
Engineers can make the concrete even stronger by stretching the bars tight before the concrete is poured. When it hardens, the steel is released, essentially compressing and strengthening the concrete.
Pre-stressing allowed architects to build bigger and bolder designs. Dr. Bound Isake, who later consulted on the iconic structure, explains.
The technique itself was fantastic at that time. The structure could not have been erected if post-tensioning or pre-stressing steel would not have been available at that time.
The pregnant oyster stood proud, hosting concerts and events for over 20 years, until one night disaster struck. On May the 21st, 1980, Berlin's famous Congress Hall began to crumble.
It was night and it was dark. And all of a sudden, a big crash happened and the roof collapsed, and it collapsed towards the street.
Filmmaker Carsten Krug raced to the scene.
I heard on the radio, a big accident happened at the Congress Hall, a famous building in Berlin, well known to all over the world. So I took my Super 8 camera, my bike, and I went here to film all what happened here.
Carsten's footage captured the carnage.
I learned more and more here. I saw a red car, which was pulled from the accident to the street here. Many people were shocked, and it seems to be ghostly quiet here. It was unbelievable. All the people was so calm and quiet.
It wasn't just those who witnessed the catastrophic scene who were left in shock. The whole of West Berlin was in disbelief.
It had an incredible impact on Berliners, as it was the first collapse after World War II. And it was, hard to say, it was like an open mouth, an open wound.
Earlier that evening, the venue had been packed with concert goers. Although the crowds had left the building, tragically, one man was killed by the collapse. In the wake of the catastrophe, engineers needed to find out what had brought this iconic roof crashing down. Parts of the damaged structure were brought here to Germany's Federal Institute for Materials Research and Testing. Dr. Isaki and his team of experts discovered not one, but two types of corrosion.
This is an original post-tensioning member. When you look at it, you see there is the duct, and in the duct there are the high-strength steels. The steels were attacked. After the duct has been rusted through, hydrogen occurred, and the hydrogen was taken up or picked up by the steel, and the hydrogen embrittlement led to fracture of the steel.
With the pioneering roof, 2 decades of exposure to wind and cold, combined with internal stresses, triggered a form of corrosion known as hydrogen embrittlement. This phenomenon is caused as hydrogen atoms are absorbed into steel. They combine to form gas molecules, making the metal brittle. A failure of this type is very hard to detect and can result in a sudden and unexpected failure in a structure. However, in the case of the Berlin Congress Hall, there were visible signs that another form of corrosion was taking place.
There was just a little bit of rust staining on the surface, but people didn't expect that. Today, you know, every structure of this type is monitored. People go there, look at it, study the behavior, check it, and then make a decision if the structure still is safe or something has to be done for rehabilitation of the structure.
Rust is much more common than hydrogen embrittlement. And once it takes hold of the steel in pre-stressed concrete, if left unchecked, the material will fail. With the Congress Hall out of action, engineers were tasked with its repair. It took 4 years, but eventually the iconic roof was rebuilt in all its glory. To avoid a catastrophe like this from ever happening again, Dr. Isaki's team is responsible for keeping a close eye on Berlin's pre-stressed concrete.
When we find cracks on such a kind of steel that is removed from a structure, this structure is unsafe because the cracks that have a small dimension at the time when we remove it from the structure may grow. And therefore, we make the decision and say, no, close the structure, otherwise you will see problems in the future.
Today, the Pregnant Oyster stands proud, hosting more than 50 large events a year.
While the building may have suffered a terrible collapse, it has outlasted the regime it was built to challenge.
Through urban development, engineers dream of making their mark on a city's skyline. But focusing on form over function can be a recipe for disaster. Like Denmark's troubled bridge over calm waters.
There's something inherently wrong in the design and the engineering of this bridge.
This bridging beauty just wouldn't come together.
They just couldn't meet in the middle.
Copenhagen, a city with a rich history that today takes pride in its modernity.
Copenhagen has everything from striking historical architecture to cutting-edge contemporary structures.
When it comes to design, the Danes are famous for uniting form and function in the most innovative ways.
Local journalist James Clasper has lived here for 4 years.
Copenhagen is the capital city of Denmark. It's one of the most livable cities in the world. It's incredibly sustainable, it's incredibly green, it's a delightful place, it's beautiful. The name literally means in Danish, merchant's harbour. Why? Because there's loads of water since the 17th century. It's been a bustling city full of ships, full of boats. And now it's a sustainable city that's trying to get its people around by bicycle. And on a city built on water, the best way to do that is on bridges.
And it's Copenhagen's newest bridge that has everyone talking.
We're coming out of Nyhavn, the new harbour. It's actually from the 17th century, but we're coming into the main port of Copenhagen. And here is the inner harbour bridge. It's also known as the Kissing Bridge. The bridge was part of an ambitious plan to connect the entire city by cycle, lane, and bridge.
In 2016, the eye-catching Inner Harbour Bridge opened to pedestrians and cyclists, connecting the city centre with the Christianshavn district. Urban consultant Michael Colville Anderson works with cities worldwide on cycle-friendly projects.
It's the most obvious location for a bridge. Right to the heart of the city is where this leads. The best thing about it is you can actually look around the city, look at the harbor front, see all the action. Quite nice.
The innovative design tackled an age-old problem for the city's bridges: water traffic.
The bridge crosses the inner harbour, so it has to be able to open for tall boats to pass through. Instead of a lifting or swinging bridge, the engineers opted for an innovative sliding bridge called a thrust bridge, with 2 retractable arms that meet in the middle.
Engineer Brendan Walker explains.
Some bridges open and close, like this. There are other types of bridges which can swing open. But what they decided to do was to create a new mechanism, which is why it's called the Kissing Bridge. The 2 halves slide in and back out again, just like a kitchen sliding drawer.
We're coming under the bridge now. You should be able to see part of the rolling mechanism, which allows these 2 retractable parts to move backwards on each side, while a larger ship with its huge mast, of course, is able to pass through.
This simple concept on a huge scale was designed to create clear passage for shipping when open, while appearing as a seamless crossing when the arms are closed.
To ensure that the decks are perfectly aligned when the bridge is closed, architects used a very simple bolt and hole arrangement, with 1 large bolt on each side, working much like dowels in woodwork.
So this is really the epicenter of the bridge. This is the entire concept right here. The nickname was the Kissing Bridge. It would sort of grind backwards and open and grind back, but gently kiss right here in the middle.
Although everything looks good today, construction didn't go as smoothly as planned.
This bridge was supposed to open in 2013, but there was a problem. The retractable arms wouldn't close properly. The kissing bridge wouldn't kiss.
The engineering of it simply didn't work. We've had open and closed bridges in our cities for like hundreds, thousands of years, and somebody decided they wanted to reinvent it. But this is really where the problem was.
It's rumored the bolts on one arm of the bridge didn't marry up with their designated holes on the opposite side by as much as 7 centimeters or 3 inches.
There's no footage of the failure, and the exact cause is still hotly debated. But the most likely theory appears to point to environmental factors.
No one's saying for sure why the two sides wouldn't meet, but one theory is that they were deforming because of an unanticipated temperature difference. Hot sun above, cold water below, causing the bridge to warp.
During construction, this temperature differential could have been causing expansion of the drawspan sections of the bridge that hadn't been predicted in the design phase.
An arm of the bridge in profile looks like my arm, thin in the middle and thicker at the end. It means there's less metal in the middle, which makes sense that any thermal effects could be exaggerated.
Take a cool expanse of water below, take hot beating sun above. We know that hot things expand, cooling things contract, and that can make things bend downwards. And under those conditions, if both sides are starting to bend downwards, they're never going to meet in the middle. And this was a massive engineering challenge to solve before the kissing bridge could finally kiss.
It took engineers 3 years to fix the bridge. And although the exact reason it failed in the first place remains shrouded in mystery, it's possible the solution was very simple.
One solution could be having wider holes or making the connecting bolts pointed or conical. That way there's more tolerance for misalignment. Once the tip is aligned, even with a small amount of warping, the conical shape would guide the decks together.
The engineering solution they came up with was to redesign the locating lug. On one side of the bridge, there's a locating hole. On the other side, a locating pin. They made the hole bigger, they made the pin smaller and pointier, making it easy for it to find a home.
It may now meet in the middle. However, the crossing still has its issues, particularly for Copenhagen's cyclists.
We bike a lot in Copenhagen, but really, this bridge is too steep. This bridge doesn't need to be this steep from an engineering perspective or design perspective. It could be much, gentler in its slope. But then you got to do these weird kind of turns, these little chicanes.
Steep gradients, slippery surfaces, and hazardous chicanes all add up to a bit of a nightmare.
This is really everything you need to know about the design of this bridge. Every time I'm here, there are new, fresh skid marks. You can almost smell the burned rubber. It has been like this for 3 years. People come over the bridge at speed, and they realize at the last minute, oh, I gotta do a quick little chicane off to the left. Uh-oh, hit the brakes. The city, after the fact, had to put up warning signs, red and white reflective material to warn people not to go straight. And there is literally a skid mark that ends right at the glass, and there always is. I've not heard of any cyclists, taking a dive over the glass just yet, but, it's gonna happen some days.
Clearly, there are several engineering lessons to be learned from this bridge. Fortunately for the people of Copenhagen, there are lots of other crossings to choose from. When building on or around water, engineers always have their work cut out. The smallest mistake can lead to the greatest catastrophe. Like here in the Golden State, where this dramatic failure threatened an entire region.
No one saw this catastrophe coming.
I had never seen it. I don't think anybody in the United States had ever seen it. It was a horrendous sight.
A disaster that spurred an industry into action.
This lucky escape revealed an engineering fail hidden in dams across America.
From the Sierra Nevadas to the Pacific Ocean, the California climate is known for one thing: sunshine.
The dry climate brings problems of its own, with vast swathes of farmland and huge cities demanding water. Keeping a ready supply is a constant challenge.
To regulate water supplies, California has a long history of building dams. One of the most crucial is the Folsom Dam across the American River. This dam was designed to do more than provide water to the surrounding area. Former regional dam manager Tom Aiken explains.
Folsom Dam is actually critically important, mostly here in the Sacramento area, for flood control. But in addition to flood control, we provide a lot of the water that feeds this urban area. In fact, you'll see pipeline over here that goes over to Folsom. Pipeline over there goes over to Roseville and eastern Sacramento.
When completed in 1956, the 430-meter-long, 100-meter-high dam created Folsom Lake, holding back more than 500,000 Olympic swimming pools worth of water.
Dams are under constant pressure from the water behind. That should be no problem. It's what they're designed for. But if the water levels get too high and spill over the dam, known as overtopping, there's a risk the dam will erode and potentially collapse, causing catastrophic flooding downstream.
To prevent this from happening, most dams include a safety feature known as spillways. At Folsom, the spillways consist of 8 concrete chutes, each controlled by a gate, allowing dam operators to precisely control water levels in any conditions.
Folsom has 5 operational gates and 3 emergency gates. The emergency gates have the flip bucket there.
Like thousands of dams worldwide, the spillways are controlled with what are known as radial gates. It's a simple but effective layout, as dam engineer Steve Melovic explains.
Well, the radial gate works. It has 2 bearings and a curved plate. And imagine that the lake is right here, and a chain, 2 chains lift this gate up just like this and let the flow out on the bottom.
The curved design of the vertical section helps the gate to better withstand water pressure.
And so when the lake just rides up on the gate, this opens up and lets the water flow underneath.
The radial gates on the spillways at Folsom operated smoothly for decades. Then, on July the 17th, 1995, dam operators planned to release water from the lake for routine maintenance. But as gate number 3 was opened, things did not go according to plan.
Our operator went up to open the gate, and when the gate got up about 2.5 feet, he said it started vibrating, a very unusual vibration. And he looked down, and at that point in time, the gate actually failed. Bolts popped, and the struts gave away, and the gate swung open like a garden gate.
Gate number 3 was severed open.
It was a horrendous sight. There was angled steel, and water was shooting out in multiple directions. So the whole face of the dam just looked like white water, a big white waterfall.
Dam operators had no way of closing the gate.
With the gate wrenched open, there was no way to stop the water pouring out over the coming days. 40% of the Folsom Lake gushed down the spillway. The big worry was that the excess flow would overtop the next dam downstream, the Nimbus Dam.
Overtopping this dam could destroy the Central Valley's last line of defense and flood the entire region. With water gushing uncontrollably from the Folsom Reservoir, it was crucial that the Nimbus Dam was prepared for the unexpected flow heading its way.
It was critically important for our operator to get down to Nimbus Dam He took immediate action, jumped in his truck, and headed down to open the gates there so we wouldn't overtop that dam. Had he not done that, then Nimbus Dam would have been overtopped, and that would have caused damage to 18 gates, plus it would have flooded the power plant down there.
Thanks to the quick actions of the Folsom Dam operator, catastrophic flooding was averted. With the imminent danger now over, engineers were left asking what had gone wrong with this decades-old, reliable system. It turned out to be a very basic but potentially lethal engineering oversight.
The investigation found that right back at the design phase, engineers hadn't factored in something called trunnion friction, basically resistance to opening at the hub.
Forensic engineer Chuck Howard investigated the accident.
There's a pin that goes into a bearing, a brass bearing, and when it's smooth and it's lubricated, it moves very easily.
A trunnion bearing system allows a shaft to rotate from a fixed point in a similar way to a ball and socket joint. In this case, the shaft is connected to the radial gate. Smooth operation of the gate relies on fully functioning trunnions. However, the trunnions at Folsom had a problem.
So think of some oxidation doing that, and that as that oxidation built up over the years, that trunnion friction increased. At the time when that gate at Folsom went up, it decided they'd had enough. And we had that one brace fail, and then it just multiplied itself to the other arms.
When they attempted to raise the gate, the corroded bearings were essentially jammed, and with the gate struggling, the force of the water from the reservoir snapped the support struts, leaving the gate wide open.
If you held on to one of these bearings like I'm doing and held onto it tight and then tried to lift the gate as the hoist would lift the gate, it makes it hard to lift the gate, right? And these beams are going to start to feel stress. They're going to want to bend because I'm holding on really tight to this bearing. So a little bit of corrosion and friction on that bearing translates to a big stress because it's a very big gate, and it caused it to buckle and for this entire part of the gate to start to move away from the dam and cause the failure.
There were 7 other identical gates at the dam. To avoid the exact same failure from happening again, all of them would have to be replaced. This time, thanks to major advances in materials technology with corrosion-proof bearings.
We ran a series of tests on this trunnion to understand that slow-moving and heavy load application of the bearing, and we learned some new things about the type of grease you should use.
It took 2 years and cost millions of dollars. But by November 1997, the new gates were in place, and the dam was fully operational again. But engineers knew there were hundreds of other dams across the country with the old-style trunnions, a ticking time bomb waiting to fail.
This epic engineering fail led to a mass inspection of dams with similar gates across the US. A program of repair or replacement was rolled out, and, in theory, the risk of any more disasters like this has been averted.
Folsom has become a case study for dam engineers worldwide. So hopefully, a catastrophic fail like that of 1995 will never happen again.